Hello everybody and welcome to exercise 4 on page 27 here. And this exercise that we're about to work through is going to lead us to a theorem on the next page. Let's read this and work through it together. So they'd like us to consider the vectors u equal 1, 2, 3, v equals 3, 4, 2. They're giving us a three-dimensional sketch of what those two vectors look like. And then let S be the set that just contains those two vectors. Okay, and the first thing they'd like us to do is to describe the subspace span of S geometrically. Okay, so in other words, if we thought about all of the possible linear combinations of u and v, what would we get? Okay, well, let's start with the definition. Okay, so the span of S is by definition just the set of all linear combinations that we can form. Okay, all of the vectors that we could build using u and v as our building blocks. Okay, where a and b can be any scalars. Okay, so we could think maybe for a minute about what possibilities we might get. So for example, if we let a and b both be 0, we would just get the 0 vector. Okay, or if we let a equal 1 and b equals 0, we would just get u. Or a equals 0 and b equals 1, we would get v. Okay, and if you just kind of think of all possible coefficients that you could make here, you're going to get things like u plus v, 2u, 2v, just any possible linear combination that you can imagine. Okay, and so on. All right, now I'd like to see if we can make sense out of this geometrically. What would this look like if we started plotting all of these vectors that we're getting in this span? Well, let's try to sketch a couple of them. Okay, so we've already got v in our diagram. Okay, what would 2v look like? Well, it would just be a vector that's twice as long, so it would kind of take us to that position, and then 3v would put us there. And similarly, if we start with u and take 2u, there's another vector that's in our span, 3u, and we can keep going. But what's interesting is that we can also do things like this. We could start at the vector u and then add v to that, which would take us here, and then add another v to it, which would take us here, and so on. And we can keep doing this. Okay, just adding the vector v to all of these things. And the question is, what kind of a shape are we generating here? Okay, you might look at this and notice that this is a flat surface. All of these linear combinations lie in a plane that contain u and v. Okay, so in words, we could say the following. Geometrically, span of S is a plane in R3 that contains the vectors u and v. Okay, there's the first part. Just kind of gives us a geometric idea of what we're talking about here. Okay, and then onward to part B here, and this asks us the question that's going to ultimately lead us to the theorem on the next page. Okay, let's imagine that we have a third vector w in R3, and they're asking us under what conditions would the set S union with V be linearly independent? Okay, so it's kind of like asking if we take the set S, which has just the vectors u and v in it, and we throw in a third vector v, under what circumstances is that new set going to be linearly independent? Okay, I want to just make sure that you realize before we dive into this that S union W would just be a 3-vector set that would look like this, U, V, and W. We're interested in when that's linearly independent. Okay, so let's explore this a little bit. Okay, it's maybe a little easier in this case to think about the question the other way around. When would the set be linearly dependent? Okay, well, notice that if W were a vector that lies somewhere in this plane that we had, maybe it's there, then it must be possible to write W as a linear combination of u and v. That would suggest that if the W we take is in the span of u and v, then we're going to get a linearly dependent set here. Let's see if we can confirm that algebraically. Okay, so if W is in the span of S, that's just another way of saying that it lives in the plane, the way that we drew up here. By definition, that would mean that W can be written as a linear combination of U and V, okay, for some A and B and R. We don't know what they are, but we know that they exist. But notice that we can take that equation and get all of the vectors on one side and the zero vector on the other. So we could rewrite this like this. AU plus BV plus negative 1 times W is equal to the zero vector. Okay, but notice what that says. We just took a linear combination of U, V, and W and got the zero vector, and notice that it's a non-trivial linear combination because that third coefficient is not zero. Okay, so here's what we can say. So if we start with the assumption that W is in the span of S, that's what we did. We just demonstrated that S union W has to be linearly dependent. Okay, well, what's interesting is it turns out that the converse of this is also true. Okay, let's just briefly explore that here. So suppose that W were not in the span of S. Okay, well, if that were true, where would it be? I'm going to just scroll up to our picture again. If W were not in the span of S, that would mean that it would be outside of this plane, kind of sticking up maybe over here in this direction or something like that. Okay, well, if that's the case, I'm going to just write down a claim here, and I'm going to leave it to you to think about this statement. Let's first kind of emphasize what we said geometrically. W not being in the span of S means outside of the plane. Okay, and here's my claim. It seems plausible that would mean that S union with W is linearly independent. I'm going to use that abbreviation Li again, because S is linearly independent and W cannot be written as a linear combination of U and V. We know it can't be a linear combination of U and V because we made the assumption that W is not in the span of S. It's outside of our plane. Okay, again, I'm going to let you think about that statement and why it might be conceptually reasonable. Okay, but turns out that this is true, and so here's what we've demonstrated. And here's our conjecture. We haven't proven this. We're just kind of making a guess based on this one example. We therefore conjecture that S union W is linearly independent if and only if W is not in the span of S. If you look carefully at the two arguments that we made above, you put those together and you kind of come up with this statement. Okay, that turns out to be true in general, and we will state that as a formal theorem in the next video.